Hello everyone, my name is Xiuhan Wang. The topic of my talk is range avoidance for no-depth circuits and connections to pseudorandomness. This is a joint work with Venkatesan Goswami and Xin Lui. So let's start by defining the range avoidance problem for circuits. Suppose we have a circuit C with n input bits and m output bits. Suppose m is larger than n, then by pigeonhole principle, there must be some length m string that lies outside the range of C. The goal of the range avoidance problem is to find such a string. We call m a stretch of C. Note that a random guess succeeds with probability at least 1/2. In this talk, we will only consider deterministic settings. In this talk, I will talk about this problem from several aspects. First, what is the complexity of the problem? The problem in general might be hard, but if we restrict the circuit class to be simple, or restrict the stretch M to be large, can we find some efficient deterministic algorithms? Second, why do we care about this problem? We are interested in its relationship between other problems, like if we give an algorithm for avoid, can we show something surprising? Third, you might notice the pseudorandomness in the title of my talk. How does pseudorandomness kick in? The avoid problem is essentially a derandomization problem. So what is the relationship between it and pseudorandomness? It turns out this problem is a canonical derandomization problem. In particular, the recent work by Cotton demonstrated that if we can deterministically solve avoid for general polynomial size circuits, then we can obtain explicit constructions of many important objects in computer science theory and mathematics, including rigid matrices, truth tables of hard Boolean functions, optimal Ramsey graphs, two-source extractors, and pseudorandom generators. There are many more examples. Essentially, a deterministic algorithm for avoid implies explicit construction for every desired object, whose existence is proved by the probabilistic method. These reductions put avoid in a central position among these notoriously hard explicit construction challenges that have been open for decades. Cotton's result is exciting. From different perspectives, we can gain different insights from his reductions. From a complexity theoretic viewpoint, this result suggests that avoid might be very hard. It characterizes generalization in the following sense. Roughly speaking, avoid admits a deterministic solution, if and only if we can derandomize the probabilistic method. From an optimistic viewpoint, these reductions inspired us to approach explicit construction problems by solving avoid. One limitation of Cotton's result is that it only considers general polynomial size circuits. Indeed, people have essentially no powerful tools to reason about Boolean circuits. However, for some weak circuits, such as constant depth Boolean circuits, or small size formulas, people do have a better understanding. This motivates us to consider avoid for simpler circuit classes. Let's define NC1 avoid and NC0K avoid. We say a circuit C is an NC1 avoid instance if each output bit of C is computed by a log-depth circuit over inputs. Similarly, we call C an NC0K instance if each output bit depends on at most k input bits. The recent work by Ren, Senserzan, and Wang surprisingly shows that a deterministic algorithm for NC04 avoid would imply surprisingly strong circuit norm bounds. Specifically, they show that a deterministic algorithm for NC04 avoid of stretch n plus 1 implies an algorithm for NC1 avoid, which further implies that there is an exponential time computable function that does not have a Boolean circuit of sub-polynomial depth. They also have a similar reduction for AC0 avoid. This result shows that a deterministic solution for the seemingly tractable problem of NC04 avoid already implies some unexpected and exciting consequences. It provides one more strong motivation to study avoid of restricted circuits. In this work, we try to study avoid from two directions. On the one hand, we want to reduce more explicit construction problems to avoid of simple classes. On the other hand, we aim to understand for which classes of circuits can we solve avoid efficiently. Ultimately, we would like to identify a circuit class C. Our hope is that C can be expressive enough so that we can reduce implicit constructions to C avoid. At the same time, C should be simple enough so that we can develop an algorithm to solve avoid, and thus solve the implicit constructions. Here is a summary of our results. In this work, we mainly focus on avoid of no-depth circuits. Following the two directions we just mentioned, we obtain the following results. First, from the above side, we reduce constructions of rigid matrices, linear codes matching the GV bound or the least decoding capacity to avoid of NC1 circuits. By the RSW reduction, we can further reduce the problems to avoid of NC04 circuits. Second, from the below side, we give a polynomial time algorithm for avoid of NC02 circuits. The only gap here is NC03 circuits, and its complexity remains an interesting open question. Third, which is the most exciting part, we give a pseudorandomness-based framework to solve avoid. We show that a wide range of no-depth circuits are bad samplers. They cannot sample a pairwise independent distribution under any input distribution. Taking advantage of the weakness of sampling gives a polynomial size heating set construction for avoid. We remark that a heating set implies a simple FP to the NP algorithm for avoid. Let's talk about our first results. In our first set of results, we reduce several representative explicit construction problems to NC1 avoid. In particular, we consider the following three problems. The rigid matrix asks us to construct an n by n matrix A such that any matrix of sublinear rank is n squared over log n far away from A in Hamming distance. This is a well-studied problem in complexity theory. Despite decades of efforts, the best known construction is still far from achieving the dream parameters. We also consider the explicit constructions of binary linear codes matching the GV bound. Roughly speaking, we aim to find a linear code with the best possible rate distance trade-off. Due to the recent breakthrough result by Tashman, we now have a nearly optimal construction of such codes. Still, there is a gap between the best known explicit construction and what is warranted by the probabilistic method. Lastly, we consider constructions of binary linear codes that achieve this decoding capacity. For all three tasks, we show that they reduce to NC1 avoid. This is to say, a polynomial time deterministic algorithm for NC1 avoid implies the explicit constructions for all three objects. Furthermore, combining our reduction with the RSW construction, these questions further reduce to NC04 avoid. Before talking about our reduction, let's first review how Cotton reduces the rigid matrix constructions to avoid. Suppose we have a circuit C whose number of input bits is less than the number of output bits, and any non-rigid matrix is in the range of C, then any solution to avoid C is an explicit rigid matrix. The remaining problem is to construct the circuit C. By definition, a matrix M is non-rigid if it can be written as the sum of a no-rank matrix and a sparse matrix S. We know a no-rank matrix can be further decomposed to the product of an n by epsilon n matrix L and an epsilon n by n matrix R. To encode L and R, we need two epsilon n squared bits. To encode S, we can store its non-zero positions. Encoding the row and the column needs log-n bits, so encoding the whole S needs 2 log-n bits times the number of non-zero entries in S. In total, the number of input bits is just 2 times epsilon plus delta times n squared, and the number of output bits is n squared. The circuit C just passes its inputs as the encoding of LRS and calculates the matrix M. If epsilon plus delta is less than 1/2, the number of input bits is less than the number of output bits, and the resulting instance is a valid avoid instance. The reduction has some drawbacks. Decoding a sparse matrix needs a circuit of O(n) depths, which is too large to suit our purpose. In the following, I will talk about how to reduce the circuit depth. Here is a key observation. We don't need to encode the sparse matrix optimally. Note that the gap between the number of output bits and input bits is a small constant times n, so we can tolerate a small O(n) overhead when storing the sparse matrix in order to support fast decoding. That's how the succinct data structure comes into play. We use the succincter result by Petrusov, which has overhead O n over log square n and query time O log n. Thus, we can find out an entry of S in O log n depths, and the matrix multiplication also takes O log n depths. In all, the circuit depth can be reduced to O log n, and the circuit becomes a NC1 circuit. Finally, by the RSW result, we can reduce explicitly constructing rigid matrices to avoid of NC04 circuits. Now, let me talk about our second result. That is, we give a polynomial time algorithm for avoid of NC02 circuits. Recall that an NC02 circuit is a function that depends on at most 2 input bits. We know there are 4 types of such functions: constant functions, functions depending on only 1 bit, and OR type functions, and XOR type functions. The main idea is simple. Our goal is to find an output Y such that it has no pre-image. We try to fix the bits of Y one by one, and each step we make the pre-image set smaller. If we can halve the number of the feasible X in each step, we will eventually get to the state where the pre-image is empty. Now, let's deal with the 4 cases. If Ci is always 0, then we can set yi to be 1 and we are done. If Ci only depends on some x, say Ci equals to x1, then we can set yi to be 0, and then x1 must be 0, and we can remove x1. If the Ci is the OR of x1 and x2, we can set y to be 0, and then x1 and x2 must be 0, and we can remove them. If Ci is the XOR of x1 and x2, then we can set y to be 0, then x2 must equal to x1, and then we can remove x2. In each step, we remove 1 output bit and at least 1 input bit. As the number of output bits is larger than the number of input bits, we can always find a solution. Now, let me talk about our third result. We give a pseudo-randomness based framework to solve avoid. The construction contains two steps. First, for some simple circuit classes, like NC0K circuits or no-width CNF-DNF, we show that they fail to generate a pairwise independent distribution under any input distribution. Second, we show that we can indeed generate the pairwise independence distribution by a short seed if we have more computation power. That is, we can find a pairwise independent set of small size. Then we claim that this pairwise independent set is a heating set for a void. Suppose by contradiction it's not a heating set, so the entire set lies in the range of C. By choosing appropriate input distribution, the output distribution will be pairwise independent sets, contradiction with our claim. Moreover, the set size is polynomial in M, so we have found a polynomial size heating set for a void. The second step is quite standard, and there have been some works about it, so we only discuss the first step. We get inspiration from the paper by MST. Suppose L is a set of functions and each Ci is biased to some function f in the function set L under the uniform input distribution. Then they prove that when M is large enough, there must be some ij such that Cix and Cjx are epsilon correlated. That is, under the uniform input distribution, the output is not pairwise independent. In our setting, we set the set of functions to be the parities of at most d variables. However, note that our setting is over any input distribution instead of the uniform distribution. So here is our definition. We define a circuit is d delta simple if the function is at least delta biased to the parity of at most d input variables over any input distribution. We show that when m is larger than omega n to the d, there must be two output bits that are correlated. So if the circuit is d delta simple, any pairwise independent set is a heating set for a void. Now the goal becomes to prove a circuit is d delta simple. Let's see two applications of this approach. First, for NC0K circuits, that is, every output bit depends on at most k input bits, we can prove by Fourier analysis that every non-affine function is k-1 2 to the minus ok simple. If there are n plus 1 affine functions, we can find a linearly independent set. In this setting, when m is larger than omega n to the k-1, any epsilon biased set is a heating set for a void. The second result is about constant width CNF DNF. Suppose the width is W, and if m is larger than omega n to the W, any pairwise independent set will be a heating set for a void. We have some further applications by relating our framework to the concept of approximating degree. The epsilon approximating degree is a function f. Defined of a function f is defined to be the least d such that there is a degree d polynomial p such that p and f are epsilon close at any point. We have the following theorem. If the 1 minus epsilon approximate degree is at most d, then f is d epsilon over 3 times n to the d over 2 simple. The proof is done by Fourier analysis. Suppose p hat is a Fourier expansion of p. By Parseval's identity, the square sum of p hat is the expected value of p squared, which is at most 4, since fx is plus or minus 1 and px is 1 minus epsilon close to fx. Then, by Cauchy-Schwarz inequality, we can bound the L1 norm of p hat. By assumption, we know that fx times px is at least epsilon for any x. So the effective value of fx times px is also at least epsilon. Then we expand B by its Fourier coefficients and apply averaging principle. Then we know f is best to the parity of at most d variables. There has been a line of work about the approximate degree of certain circuit classes, and we can apply these results in our framework. For De Morgan formula of set S, if m is larger than n to the omega square root s, there will be a polynomial set heating set. For unbounded with CNF of or DNF of set S, if m is larger than n to the omega square root n log s, there will also be a polynomial set heating set. We also note that the paper by RSW also designed AP to the NP algorithm for De Morgan formulas with a large stretch. However, their algorithm is based on the algorithm method for proving lower bounds, which is very different from our framework. Interestingly, their algorithm also used the approximate degree upper bound of formulas as a key technical ingredient. However, their framework cannot exploit large error approximate degree upper bounds to yield algorithms. In particular, their result does not directly apply to small width CNF or DNFs as our result does. We also remark that a heating set construction appears to be slightly stronger than an FP to the NP algorithm, because given a small heating set, we can test each string in the set by issuing parallel queries to the NP oracle, whereas the RSW algorithm needs to use the NP oracle in an adaptive fashion. However, the assumption considered in our framework is not comparable to theirs. Just to wrap up, in this work, we studied the range avoidance problem for no-depth circuits. We reduced several explicit construction problems to avoid of log-depth circuits, which can be further reduced to NC0 for avoid by the recent RSW reduction. We give a polynomial time algorithm for NC0 to avoid. We also propose a pseudorandomness-based framework to solve avoid of simple circuits with large stretch. As applications of our framework, we designed non-trivial heating sets and AP to NP algorithms for avoid of various low-end models, including NC0K circuits, DNFs, and De Morgan formulas. We conclude with several interesting open questions. First, by the RSW reduction, we know NC0 for avoid is probably very hard. We also have an efficient algorithm for NC0 to avoid. It would be interesting to figure out the complexity of NC03 avoid. Second, we want to ask if one can extend our heating set framework to solve avoid for other circuit models, such as avoid of AC0 circuits. Lastly, given a class of circuits C, finding a small heating set for C avoid is itself an explicit construction problem. It might be interesting to figure out how does the complexity of this problem depend on the circuit class C. Note that if C is expressive enough, then a heating set for C avoid is in some sense a universal solution for a wide range of explicit construction problems. Thanks for your attention.